All right. Well, I'll begin with a word of prayer. So here we go. Dear Father, we thank you again for this opportunity we have just to meet and study your creation. Again, I just pray you would be glorified at what we do, and that we'd all understand a little bit more about physics today, Lord. In your name I pray, Lord Jesus. Amen. So I need to do an example before I forget. And example one basically is spring motion, but this time with details. And by that I mean I want to actually solve the equation in a little bit more depth. And so the situation we're talking about here is you got some spring, and maybe it's stretched out a little bit, right? And it's pulling on some mass, right? And so the distance that the spring is stretched from the equilibrium point is called x, right? And the spring force is equal to minus kx, right? This is Hooke's law. Fun fact, Hooke was a contemporary of Newton, and Newton didn't like this guy, and he treated him badly, if I understand the history correctly. I mean, as an example of that, Newton wrote this Principia Mathematica, which is like hundreds of pages, right? It's his master work on what we now call Newtonian mechanics. This guy was like a contemporary of Newton. Does his name appear anywhere in Principia Mathematica? Does not. So like this guy was kind of ignored by Newton in some sense. Anyway, Newton's an interesting fellow. Did I tell you guys what I learned about Newton? I don't think I did. So I've been watching some videos about Newton. And so he did not believe in the Trinity as we believe in it. So he believed that there was this Trinitarian conspiracy that began in the 4th or 3rd centuries that intentionally changed certain verses of Scripture in order to be more Trinitarian, more friendly to the doctrine of the Trinity. Now, he did work at Trinity College, so you can imagine this had to be kept on the down low, because when you work at a place called Trinity College and you don't believe in the Trinity, it's a bad look. So these things he kept secret. He wrote them, though. Even from the time he was your age, he had vast theories of these things. And pretty much all the people who were close to Newton ended up believing similar things. And he also had like a deep interest in biblical prophecy. Like the bulk of Newton's time he did not spend on mechanics. He spent on alchemy and theology, especially prophecy. He was very interested in proving that Jesus had to come to earth when he did, according to Old Testament prophecy. And most of the events, as I understand, I've not read anything, right? But apparently, like lots of the prophecies in Revelation, he saw as being things that happened in the 3rd or 4th century as part of that Trinitarian conspiracy. And he has this whole sort of almost kind of dispensationalist like charts in terms of prophecy and so forth. And here's the 3 prophecies he made. They're kind of fun. Number 1, he prophesied that, this is Newton, prophesied on the basis of Old Testament prophecy that, or possibly New Testament, that there would be a renewed interest in a Zionist movement, that is, Jews returning to their homeland, in about 1899. Prophecy number 1. Prophecy number 2. He prophesied that Israel would in fact become a nation again in about 1940. It's doing pretty well, isn't he? The third one's more troubling. He also prophesied that the world would come to an end as we know it sometime between the year 2000 and 2050. So, yeah. Lest you think he's prophesying rapture, I would remind you he doesn't believe in the Trinity, so yeah, it's kind of like finding communion with a Mormon or something. It doesn't quite make sense. They're nice people, but they don't really believe in Jesus. So, all right, now, not the Jesus we believe in, assuming you believe in Jesus. You don't have to believe in Jesus to be a student here, do you? Right? So, now, although it would be really annoying to not be a Christian and come to school here, I think, in some sense. I can imagine that being annoying. let me solve it. So this is the net force. The net force is ma, right? So we've got ma is minus kx. Now that everybody's here, we've got m dv dt is equal to, minus kx. Now, I guess we could go different ways here. You could do the v dv dv trick and solve for the velocity as a function of position. That would perhaps be interesting, but I just really want to solve the differential equation here, so let me get to it. So what we got then is m d squared x dt squared is equal to minus kx, all right? Let me rewrite that a bit. So what we're really looking at here is d squared x dt squared is equal to minus k over m times x. It's convenient to say that that's equal to like minus omega squared x, and to like let omega equal to the square root of k over m. Now k and m are both positive, so that's a reasonable step, all right? And once I make that step, I can ask you a question, which is, can you tell me a function, right? Can you tell me a function which, when you differentiate it twice, it gives you back omega squared times the function again? Sine. Sine of what, though? Good idea. So I've got to vote for x equals to sine. We'll start that as a canvas on which to draw our function here. Let's start with sine, sure. Differentiate sine 2 times, you get back a minus cosine, right? But we don't just want back minus it again, we want back minus omega squared times it, right? So let's take your sine and add a omega t to it. All right? Yeah. Is that a question or? No. Okay. And then we might as well just add a phase angle like delta here and an amplitude a. Check it out. So here, so anybody in here currently taking differential equations? So you know what time it is. That look familiar? Not really, does it? Because, what's that? Not yet. Yeah, so to make this look differential equation z, I would do this. This is a cos delta sine omega t plus a sine delta cosine omega t. Recognize this as the quote-unquote C2, and this is the quote-unquote C1 in the typical solution. So like in differential equations, they teach you the solution C1 cosine omega t plus C2 sine omega t, which is wonderful for differential equations because it's easy. But for here, the equation I wrote down to start with is really better. So this is just this is only for you. This is an audience of one because the rest of you haven't taken differential equations yet, which is fine. In fact, I derived this in calculus 2 in a good semester, all right? You don't need differential equations to derive this. There's integration that you can do to find this solution. Anyway, once we have it, right? This right here solves dx dt squared equals to minus omega x, all right? And basically the meaning of the delta, it just describes like essentially the initial position of the spring, right? Like what's the initial position of the spring in terms of my solution? X of 0 would be what? It would be like a times the sine of delta apparently, right? So that's like the initial position. What's the initial velocity? If this is x, what's v? We find the velocity, we differentiate, right? So the velocity as a function of time would look like, well, a omega cosine omega t plus delta, right? So apparently the velocity at time 0 for my solution would just be like a omega cosine delta. So just to, anyway, if you want to actually find the delta and find the amplitude, if you were given an initial position and initial velocity for the spring, you could figure out what the initial phase angle delta was and what the amplitude of the motion will be. All right? Okay, so let's work out some things. What happens if we look at, let's study the quantity. 1/2 mv squared plus 1/2 kx squared. What's that going to be equal to? Let's work it out. Yeah, that's kinetic energy plus potential energy. That's right. But what is it in terms of these formulas? So we have, 1/2 m, and my v is a omega cosine. And to make life easier, guys, let us agree to say theta is equal to omega t plus delta. Just save us a bunch of writing, all right? Theta is omega t plus delta. So I've got a omega cosine theta, that thing squared, right? Plus 1/2 k times x squared, which is what? A sine theta squared, right? And so what goes on here? What's that equal to? We've got m a squared omega squared cosine squared theta plus 1/2 k a squared sine squared theta. Can you guys tell me if these terms combine or anything? Like, what's the situation here? What's omega squared equal to? Right, that's k over m, right? Okay. So what happens there? See that? This m, it cancels that m, so they're actually both the same. They're both 1/2 k a squared terms. So really, in view of that algebra, we have 1/2 k a squared times cosine squared theta plus sine squared theta. In other words, we've got 1/2 k times a squared. Does that depend on time? It does not, right? K is a constant, A is a constant. What is A? A is the amplitude of the motion. A is the amplitude of the spring motion. K is the spring constant. This, of course, is energy. So we have that the total mechanical energy is actually equal to 1/2 k times the amplitude of the motion squared. This is not really surprising because if you think about it, that really directly comes from what? Putting the potential energy equal to the max, right? It's like if you think about it, there's two sort of extreme situations, right? When it's stretched out all the way to its maximum x max, right? That's what we call the amplitude, right? In that situation, the potential energy is 1/2 ka squared, right? And in that situation, that's equal to the total energy. Because the kinetic energy is what? It's 0 in this situation when the spring is totally stretched out, right? Or when it's totally compressed. Same story, but with x equal to minus a. But what should the other part of the story be? If you think about the case that the mass is just coming through, like it's right when x is equal to 0, that should be either this way or that way, the maximum velocity, right? So the energy should also be equal to what? It should be equal to, 1/2 m v max squared. What would the maximum velocity be? If you look at our formula, what's v max? It would be this, we have a omega, right? So the maximum the velocity could be is when the cosine is 1. And that's going to happen exactly when the sine is 0. Sine is 0, of course, at the equilibrium position, right? It doesn't have to be time 0 because we're not necessarily starting it in the equilibrium position at time 0, so that's all kind of funny. But so the maximum velocity would be a omega, right? And what would the kinetic energy be then? Let's check that out, right? So this is so the kinetic energy in this situation, 1/2 m a omega squared. What do you get? Well, what is m omega squared, as we just talked about a minute ago? See this? Omega squared, k over m. So m omega squared is k. So again, this is 1/2 ka squared. I mean, it's all consistent. So I just want to alert you to the fact that, like, for a spring, yes, we have energy conservation, but we do have a few more formulas that are interacting here in terms of, like, the mass. What do we have? I should give some names. K is the spring constant, m is the mass. Those aren't confusing. But what's the name of omega? What is this thing anyway? Can you guys tell me what its name is? Omega is equal to the angular frequency. The angular frequency. It's basically the number of radians per second in the sense of, if you, well, let me shut up about that. It's the angular frequency. Now, more to the point, if we have x of t equals to x of t plus big T, you know, the smallest t, which does this, is called the what? It's called the period, right? The period of the motion is how much time it gets for it to go full cycle back to where it started, right? So what's the period of the motion? You need for the input for sine to cycle through 2 pi, right? So in short, we can think of omega times the period should be equal to 2 pi if you think about it. So the period is actually equal to 2 pi over omega. So, like, I ask you guys to find the period of a spring in motion, right? I don't think you could figure that out just from energy conservation, right? Because energy conservation is kind of timeless. To figure out the period of the motion, you need this mathematics. So the period is equal to 2 pi over omega. What's omega? Omega is the square root of the spring constant divided by the mass, all right? I think that'll let you solve the last homework problem in the mission. I think I've given you all the necessary technology now. The mathematics here is dealt with more coherently and completely when you take differential equations here. So, in differential equations, we do other fun things like add a force pulling on the mass and let friction be involved, things like that. There you need the full ensemble of, like, second order differential equations to really solve it. Yep.
So you said we're choosing the k to be a sine omega t plus delta squared because that integrated twice is itself?
Yeah, this is a guess. I mean, when you're solving a differential equation, the question is, can you find a function that when you plug it into the differential equation, it works, right? So here, Newton's second law becomes the question, can I find a function which, when twice differentiated, gives you back what you started with times omega squared? And what we have in the red box up there does that. Yeah?
So then you could do the same thing with cosine, right? That would also be valid.
Oh yes, absolutely. That is true. And if you did that, the coefficient out in front would still be the amplitude, but the precise meaning of the phase angle would differ. And indeed, people, kind of different schools of thought, whether you want your typical sinusoid to be described in terms of a cosine shifted or a sine shifted. I've seen different books go different ways. So if you're an electrical engineer, you're like, no, I will use phasors. Instead of this, you do e to the I, or excuse me, e to the jt, j omega t, something like that. And use a complex exponential. You can use sine and cosine both at the same time. There are many choices. So anyway, I wanted to share this stuff with you guys before I forgot. So I will erase it if that's okay with you guys. Is it? Yeah. If you're wondering how to derive this with Calculus 2, I'll tell you the path. What you do is you change this to, instead of m dv dt, you change it to m v dv dx. And then you've got like v dv is equal to minus kx. You integrate that, that gives you like a v squared is equal to x squared plus a constant. But then that gives you that like dv dt is like the square root of like 1 plus x squared, which then ends up giving you like integral over the square root of like 1 plus x squared, something like that, which when integrated gives you an inverse sine. You get inverse sine equals to like t plus a constant, then you solve for the thing and you get sine. So you can do it, but it's just, yeah. Who cares for here? But mostly here, you need to know about these formulas and be able to apply them, right? That's kind of more where we're at here. So this derivation I'm erasing right now is something I would test on in differential equations, but I wouldn't test on in here. Here I just want you to know about it and be able to use it to solve problems, like the one in the homework. All right. So with that, the floor is open for questions. You guys got questions? Ask away. Everyone's already done with their homework? That's good. Yeah? No?
Just one thing about the way you derive the thermal energy. Basically, all you're saying there is that when the with the blue marker, when the kinetic energy is equal to 0, then that's just a rewritten version of the potential energy equation. Because a squared is the same as x squared when the x is the maximum. Yeah, so it's the same equation.
Right. Yeah, like this, it is always the case that the total energy is 1/2 Ka squared. You can understand that in terms of maximum potential energy from the maximum extension or compression, or you could understand it in terms of maximum kinetic energy at the point where it goes through the equilibrium, because even there also, kinetic energy is 1/2 Ka squared. And then anywhere in between, it's an amalgam of both. Yeah. Anywhere, and we actually could write it as a function of time if you go back to the things I erased. You could specifically write how much kinetic, you could write kinetic energy as a function of time and potential energy as a function of time if you use the formulas I just erased, but because they're changing, right? The kinetic energy and the potential energy are changing, but the sum of them is always the same. All right. Who's got the first question? I mean, I can end class early. I'm just joking. We never do that. Besides, you want me to solve your homework? Yes? No? Problem 34 in the mission, I guess. What about it? What's your question about problem 34? What is the work done on the crate by the net force? I heard a vote for 0. Who else agrees with 0 and why?
We talked about it. There's the constant velocity, so there's no acceleration.
Right. So the answer for part C should be 0 because we're told at the start of the problem that we're talking about problem 34. At the start of the problem, in the preamble to it, it says that the motion's constant velocity, right? So the work energy theorem says that the net work done is equal to the change in kinetic energy. But if the velocity doesn't change, the kinetic energy doesn't change. So the change in the kinetic energy is 0. Therefore, the work done by the net force must be 0. Another way to look at it is that because you have constant acceleration 0, right? That means that the forces of gravity and the lifting force must be balanced. So the negative work by gravity is canceled out by the positive work of the lifting force. So you should also see that the answers from parts A and B are equal and opposite in magnitude and add to 0. Because we can also see the net force is the sum of the work of gravity and the work of the lifting force. We should get 0 either way we think about it. So that's 34. I think I may have answered part D accidentally, sorry. Yeah. Other questions? Yes?
From the mastery homework,
Uh-huh.
6.52.
6.52. Give me a second here. I'll try to find my way to it. Annoyingly, they're not all in order, as you know. Is that before 666? Yeah, it's right before 666. Ah. All right. Let me see if I can figure this one out. I don't know. 6.52? So here's exercise 6.52. You have an 80 kilowatt. So there needs to be like a lot less talking in here right now. An 80 kilowatt engine power. So when it, good grief. When its 80 kilowatt engine is generating full power, all right. A plane with mass 700 kilograms gains altitude at 2.5 meters per second. All right. The question then is, what fraction of the engine power is being used to make the airplane climb? All right. So how should we figure that out? So the question is, what fraction of engine power is making airplane climb? Now that's a somewhat ambiguous question, but what they mean to ask is, well, they kind of explain more in the words. Is like the rest of it is going into like air friction and other things. This is the part of the power which is going towards opposing the force of gravity, right? That's the intent of the problem here. So what do you guys think? How should we understand this? Okay, so if it gains altitude, so I guess that's the question. It's like what's the effective power here? I guess you could call it. So let's call that power. I don't know. Effective would be what? We do the force of gravity, right? Times the velocity. Now, why do I do that? What's that? Because why?
Power is force dot velocity.
Yeah, power is force dot velocity. It's because this is altitude, right? So this is the vertical part of the velocity. Yeah. Yep. What? Oh. Okay. So we got 700 kilograms times 9.8 meters per second squared times 2.5 meters per second. What's that give us? I get, 17, what?
I got this.
Oh, okay, it's fine, it's fine. 17,150. I was worried because I thought it was 8 kilowatt for a second there. I was like, wait, what? So, I mean watt. A watt is a joule per second. Yeah, by the way, watt is a joule over a second, which is a Newton meter over a second. As you can see, the units are consistent here, right? Like newtons times meter per second. Newton meter per second, also known as a joule per second, which is energy per unit time. This is the unit of power, watts, as in W-A-T-T, some dude. All right, so the effective power then is 17.15 kilowatts. K for kilo, K is 10 to the third, okay? Maybe you've experienced this in some homework problem somewhere. I haven't talked about that this much, right? This will be a much bigger issue next semester if you, for some reason, continue your physics journey with me in the next semester. Physics 2, lots more multipliers, like lots of multipliers. All right, so then the question then that we got is, so we've got the P effective by the, full power. What's that give us? Times 100%. That should give us the percentage that we're actually going towards the climb. I get 21.44% efficiency. So like, 78.6% wasted, something like that. Let's see. Yeah, I think it says to give the answer as a percentage, right? So, yeah. So it's it says for my numbers it'll take 21 or 21.4 or 21.5 or 21. They've got a selection of different numerical answers they'll choose, but I hope this makes sense. Yep. The larger story here is the power developed by a particular force is the force dot the velocity. All right. Two helpful special cases to keep in mind is if the force is directly in the direction of the motion, the power developed is just force times velocity at that instant. On the other hand, if the force is perpendicular to the motion, the power developed is 0. So those two extremes. Anything in between that's a dot product. Other questions? Oh, pendulums, yeah. Did I have a pendulum problem in there?
Exercise 5.50 is giant swing in a county fair consists of.
Oh. Yeah, that's not exactly a pendulum problem, but I see what you're saying. I think I have like a day devoted for pendulums later on, if I remember right. Where's that thing? But we can do that problem. Which one is that? 5.50. Why does it have to be so hot in here when it rains? What's the deal? Is it just me? Or are you guys like not feeling humid? I feel very humid. 550. Let's work through this thing. So it's the giant swing problem. And so you've got this contraption, and then there's 3 meters here. And then you're told that this lady here is in some seat. And the swing is swinging apparently at 30 degrees off the vertical. And the distance to the seat is 5.00 meters. So let me read the description. Giant swing at a county fair consists of a vertical central shaft with a number of horizontal arms attached at its upper end. Each arm supports a seat suspended by a cable 5 meters long from the upper end of the cable being fastened to an arm at a point 3 meters from the central shaft. All right, it says, find the time of one revolution of the swing if the cable supporting the seat makes an angle of 30 degrees with the vertical. Whoa? Am I missing something? Is that it? Okay. So that's all we have.
Well, we just find the centrifugal acceleration.
Find this. You say find the centripetal acceleration. Okay, so I guess the question is, if we think about the woman as if she is a blob right there, and then we ask, what's the free body diagram, right? What's going on? There are really just two forces at play here, right? You got your mg down, and what else do you got? You got your tension force up like that, right? That's it. Is there any other force here? And we're ignoring air friction because we always do, right? Except when we don't. Pretty much don't. Consider it. Now, you're saying it's going a circular motion, right? So like, there is circular motion to consider here because if we look at it top down, she's going in a circle, right? So that means that if we think about the circular motion, like how far is that? What is the distance? What's the radius equal to? 5.5? 5.5. Now why would that be 5.5 meters? How did you get that? 3 meters plus what? What's going on here? What manner of dark magic are you using? Ah. So yeah, this is the 5 times sine 30, also known as 2.5. So 2.5 meters for this guy, plus 3 for that gives me a net of 5.5. All right. The path is circular.
Oh, the whole thing's
The whole thing's circling around. So the path is circular. It's in a, it's in that plane above the ground, hopefully, right? If you drag the people on the ground when you swing it, you get lawsuits and stuff. So you don't want that. Now, let's see here. If I make a slightly less cluttered picture, this tension force and the gravity force, what's going on here? We can break the tension force into two pieces, right? There is this piece, and there's also this piece, which is what? T cos 30 and T sine 30, right? Now, T cos 30 and mg, these have to cancel out because why? Because the acceleration vertically is what? 0, right? It's staying in that same horizontal plane. So we, on the one hand, have that T cosine 30 minus mg has to be equals to 0. Looking at the vertical acceleration. And I'm just not as good at it as he is. No, I don't. He's got years. He has years of practice. I've grown reliant on the.
I watched him do it, and I'm like, that shouldn't be working as well as.
It does work well for him, but he has years of practice, and I've grown soft and reliant on this eraser shirt. So what can I do?
Yes, but you have
So.
to take care of the board very much.
Well, I do try. All right. So on the other hand, we have mv squared
Well,
over r is equal to the mass times the, that's the center seeking acceleration because it's going in a circle, right? Where is that acceleration coming from? The net force in that direction is what? T sine 30, right? So we have, on the one hand, tension tension is equal to mg over cosine 30 degrees, but we also have that, mv squared over r is equal to, 0.5 times t, because that's cosine of 30. So I don't know, what were we asked to find? I've forgotten.
The time of a revolution.
The time? Well, that seems tricky. The time of revolution. Well, generally when the population gains a certain amount of animus towards the government, that happens. But let's see here, so 5.50. But it only takes like 2 or 3%, right? A motivated 2 or 3%, something like that. We don't care what the tension is, right? So solve for t. T is mg over cos 30, and that's also equal to 2mv squared over r, right? Apparently the mass doesn't matter, hooray, because we weren't given that, right? And what we got? We got the velocity is what? Rg, what? Over 2 cosine 30, also known as square root of 3.
And then all that square root of
Square root of that. Great. So you guys tell me what that is. We figured out R, right? I like this problem. This problem's got lots to it. I like this problem. It's a fun problem.
5.58.
Just a second here. I'll confirm or deny your answer. You got what?
5.58, but I think actually.
No, I think you got it. That's what I got. So we got the same wrong answer. So 5.78 meters per second.
So do we do
5.578, yeah. Now, that's not the answer, is it? That's what's that? That's the speed around the circle, right?
Yep.
How do you figure out the speed? How does the speed relate to the time for the
circumference divided by velocity?
right, so we're talking about constant speed. So remember v is equal to the circumference, 2 pi r, divided by the time that you want to find, right? So solve for t. T is equal to 2 pi r over v, which for us is 2 pi times 5.5 meters divided by my, and of course you could find a symbolic answer here if you wanted to, but it's too late, I already punched the numbers. So, oh well. Like I told you guys last time, I don't always live up to my ideal. Times 2 times pi.
Isn't that about like 6?
Oh wait a minute, wrong thing. 2 times 5.5 divided by 5.578. I get 6.195 seconds. Notice the meters cancel and 1 over seconds is seconds. That makes sense. And is that what my keys? Yeah, 6.19 is what I've got in my key over here. So, yay. Question, does the angle depend on the weight of the passenger for a given rate of revolution?
No.
We didn't have the weight, so.
The mass is canceled out in this calculation.
Yeah, I don't think so. No.
The answer is
You already tried no, okay, good. I do, I am aware of the stupidity of giving you many attempts on yes, no questions,
No,
but
I'm kind of positive.
the point of view is not to get points, really. The point's to learn why you're putting no or yes there, right? So, just saying. Other questions?
5.74.
5.74. Let's see if I can find it. 5.74. Where is that thing? Oh, there it is. Aha. All right, what's going on here? In the following figure, m1 equals blah, alpha equals yada. Coefficient of kinetic friction between the block and the incline is yerk. And what are you supposed to find? What must the mass m2 of the hanging block be if it's to descend 15 meters in the first 3 seconds after the system is released from rest? All right. Let's do this thing. So we've got inclined plane. We've got angle alpha here. We've got mass 1 here. And pulley over here. I've got mass 2. All right. And coefficient of kinetic friction. Let's see here. For me, I've got M1 equals to 20 kilograms. I've got alpha equals to 51.6 degrees. And I've got a mu sub k equal to 0.4. All right. So the game plan here is to write down Newton's law by sorting through the free body diagram, solve for the acceleration, and then use kinematics to answer the question. So what's going on here is you've got your normal force, like so. You've got your m1 g cosine or sine?
Cosine.
Cosine alpha, very good. You got your m1 g sine alpha going down here. The force of which way is the motion going? Did it say how the force is it going this way or is it going that way? Did it say? Going to the right? All right, so if it's going to the right, then that means the force of friction's this way. Right? If it's going this way, the force of friction's opposite the motion. Over here, and of course, last but not least, you got your tension force, right? Tension force goes like so. Over here, you got tension, and you got m2g. That's easier, isn't it? All right, so all together. Here we go. Notice that the normal force is equal to m1g cosine alpha because those have to balance out since the mass is staying on the plane, right? So looking at the Newton's law perpendicular to the plane, I get that balancing of the normal force and that part of gravity. That tells me that the force of friction is actually equal to mu k times m1g cos alpha. All right, so I got that. On the other hand, I have m1a is equal to the tension minus mu k m1g cos alpha minus m1g sine alpha. So that's just Newton's law on m1. Newton's law on m2, because they share the same acceleration, yeah? Because they're connected by a stretchless string, which would be minus t plus m2g as it happens. You take these and add, and that gives you, after an algebra step, that you get yourself a m2g minus m1 times parentheses mu k cos alpha plus sine alpha times g divided by m1 plus m2. That would be the acceleration in this situation. Okay, so we can plug the numbers into that. Okay? But how does that help you? You said, what must have been mass m2 of the block B? Oh, we don't know. The thing is, we don't know m2, do we? But what else do we know? So let's put that, store this away. All right? For me, I'm also told what? It descends let me just say it drops 15 meters in what, first 3 seconds released from, after it's released from rest. After released, so we have what? We have YF is equal to Y naught minus 1/2 AT squared. Okay? So you can use this to calculate the acceleration. Once you know that, you can put that up here and you can solve for M2. That's how you solve this problem. We're out of time, but that's how you solve it. The answer for mine is 42 kilograms. So for me, it works out to 42 kilograms. But that's it. Uh-huh. Uh-huh.